Hello and welcome to my channel. Today I am with another episode of my Revisiting Maths for Chemist series part 2, and today is not really on maths but rather maths in combination with computation. Computation makes maths very visual and we'll explore that today. And the topic goes like from bank interest to the most beautiful equation. A poetry in the language of Excel and ForTran. So I will be touching the maths as such with a little bit of Excel and ForTran to explore some of the aspects of maths, right? A poetry. So let me start with a bank, of course an imaginary bank which gives you 100% interest rate. 100% means per annum. So if you have 100 rupees, then after 12 months you will get 100 rupees interest and the total will go up to 100 plus 100, 200. So for convenience, let me say that I have 1 rupee, and then after 12 months I will get 1 rupee in interest and the total would go to 1 plus 1, that is rupees 2. If we calculate once in a year, that means after 12 months. Now it may so happen that the bank, a better bank, decides to calculate its interest twice in a year. That means first after 6 months and then again after another 6 months. So how the calculation goes? So in the first installment after 6 months, so the interest on 1 rupee capital you will get half. So after 6 months you get 1 plus half, that is 1.5, and then in the next 6 months now you are having 1.5, so it would be calculated on 1.5 as capital and the interest would be 0.75 and the total would be 2.25, which is slightly more than 2 in the first earlier case. And now you can think of that, okay, even better bank will give you calculation of thrice in a year, that means 4 months, 4 months and 4 months. So the calculation similarly goes like this, that after the 4 months you will get this 1 plus 0.3333, that is 1.3333, and then after next 4 months you will get, by same calculation, the interest would be on 1.3333, so it is 1.7777 after 8 months, and then after 4 months another 4 months, that is after 12 months you will get, by same calculation, 2.3703, which is even larger than 2.25 or even 2. So as you know that as you see that if you split the year in more than n equal to 3, 4, 5 installments, then probably you will be getting more and more values, right? Now the question is, what happens if n is in general n, 4, 5, 6, whatever it is, n, and moreover do you expect that if I split, if n is very big, then you are going to get a huge amount for n large? So we will explore these questions. Let us make two generalizations, one in terms of x 100 percentage rate of interest, not 100, in general x 100, and another is when n is not 2, 3, 4 but n is n, and of course I will see what happens when n is very large. So the formula actually is 1 plus 1 by n whole to the power n, right? This is the general formula for n. Now we are not proving it, but let us check whether the formula is correct or not. Say for n equal to 1, that means once in a year calculation. So 1 plus 1 by 1 to the power 1, that means 2, and that we already got. So n for 2, for n equal to 2, 1 plus 1 by 2 to the power 2, and that would give you 2.25. And similarly for n equals to 3, 1 plus 1 by 3 whole to the power 3, and that gives you 2.3703. So as expected, the calculations are okay. So that we can accept this as a general formula. Now let us consider the another generalization, that is not 100% interest but x 100% interest. So the simple replacement would be like this, just 1 would be replaced by x. So the formula remains the same, only x coming into the formula. Well, what I can do, I can calculate for different x values, and of course one of the values must be 1. So I can have a different x values to calculate this term quantity for a given n. Okay, and then I can get the values of this quantity for a given n. Now what I can do, I can plot. I can plot this x versus y. This is the y values for different x. So I can plot, but that the whole thing would be for a given n. N is 2 or 3 or 4, whatever it is, for a given n. Now what I can do, the next step, I will be doing the same calculation again and will go for another plot, but this time with a different n. That means I will be now varying the n from say 1 to very large quantity. Now for this plot I am using Excel, so I will go to the Excel plot and we'll see what happens when I am varying n from a small value to large value. Well, this is the Excel plot. Here I am doing the calculations, just don't bother about that. This blue curve is static one, constant one. It will not change. It is something else. I am not disclosing it right now. But this line actually my plot or curve for this 1 plus x by n whole to the power n calculation for a given n, and n is here, for example, n is 1 to start with. So if it is 1, then of course the equation would look like that 1 plus x by 1 to the power 1, that means 1 plus x. So it's a straight line. It should be a straight line of tan 45 is 1 and with intercept 1, right? So that is okay. Now what I will do, and what one more thing you notice, that this straight line or whatever the curve is for this n equal to 1, it is far away from the shape of that of the given existing one. Why I am comparing with this one, what this one, that I am coming later on. Now what I will do, I will change this n value, say n equal to 2, and immediately we will see what happens to the calculations and to this plot. So I am just putting the value 2 and you see the curve is changing. This one is changing, but this one is static. It is not changing, nothing to do with this n value. And now I am going for a little higher value, n equal to 4. So you will see the change. Yeah, so it is approaching towards that particular line. So I just give one, say 12, and then you see it is very close to that one given one. And say for example, I am giving a big number, say 100, and it is almost the curve that I have given to start with, right? So that is what I wanted from this Excel plot to show you basically that okay. So I am leaving out of the Excel file to show you that what happens if I plot x versus this quantity for a given n and then for different n values. So that we have seen. Okay, fine. Now the question is, what is that particular curve which was static and to start with it was given, and that is okay, we can guess probably, and that's a very popular and famous one, and that curve is nothing but of a function fx, and that fx is nothing but e to the power x. So if we just plot e to the power x, that is exactly what I have plotted, and I will get that curve, blue curve. So what's the conclusion? That means that for large n, this quantity is nothing but e to the power x. So that is my conclusion. So from a simple, completely different problem of bank interest, I am getting a very beautiful expression of e to the power x, where e is a very weird number, right? Well, so let us go back to our 100% problem, not in general x, but x equal to 1. That means we will get e to the power 1. E to the power x gives e to the power 1. That means e. And here we just put x equal to 1 to get 1 plus 1 by n to the power n. So that means I am getting an the alternative expression for e. So I can have a check that whether this gives you the value of e, because the value of e is known to us. Of course, it would give only your n is very large. So in our first problem, we anticipated that probably we are going to get a huge amount of money if we split n equal to a large, but it is not the case. Actually, it would converge to e, right? E. and that would be just 2.718, etc. So we'll not get more money than this. Okay. Well, now I will explore this by computation using a ForTran program. I will just evaluate the value of E using this expression, of course taking n very large. So let me go to the please bear with me, it will take a few seconds only. Well, bank interest. Okay, so e to the power x by bank interest. E to the power x, the formula is given. I will take x equal to 1, and then of course I will take some another value. Let me run the program. Okay, so I am running the e to the power x calculation using that 1 plus x by n whole to the power n formula. Of course I will be using x equals to 1, and n can be taken high quantity, but I will give a maximum n value, and then I will go from 1 to all values, through all those values up to the maximum value. So it will not display, of course, all the results, but it will display only the last one. But in my program, it has calculated all the values for n equal to 1, 2, 3, etc. So let me give x equal to 1, and x max, say I am giving a big value 2000. So what I expect, e to the power 1, so E, I expect the E, right? So this is, it is giving 2.71 something, and exact value of E is 2.718. Of course, you can go even higher n values, and probably it would give you the more and more close to the exact value. So that is the exploration using ForTran program. And now I am going back to my PowerPoint presentation. If I put another x value, pi, suppose I will be using pi, x equal to pi. So that means it would give you e to the power pi, and that is actually known as Gelfand's constant. Here, this picture of Gelfand, 1906 to 1968, Russian mathematician, and he was a Marxist philosopher. So the value e to the power pi, exact value is 23.14 something, and again we will explore that the same program I will run again, but this time I will give the pi value 3.14, that means pi. Okay, so let me run the same program with this time a different x value, and max you can give the same as earlier. So 3.14 roughly the pi values. Okay, and 2000 give the x values, max value, and you see the calculation gives you 20.08, and it is 23.14. So you have scope to increase as much as you like. So we are approaching towards 23. So again we see that computation helps you to understand what is happening in the maths portion. Okay, so now I am going to the next slide. And that tells you that actually this e to the power 1, e to the power x in general, it was done by none other than Leonhard Euler later on. But that everything we get from two other series, and that is very much part of our UG curriculum, Maths for Chemist course. I am not going into the details of this discussion, because in another video I have discussed this in depth. So I am just giving the outline that Taylor series is nothing but expansion of an arbitrary function fx in terms of a simple polynomial, infinite series polynomial, where the c0, c1, c2, these are the unknown, and if you can determine this unknown, then you can get the expansion for any arbitrary function fx. And the Cn, the formula goes like this. It involves the nth order derivative in general at the value a, because you are expanding the function around a, and this is factorial n. So that is Taylor series. But if you put a can be any value, but if you select a to be 0, that means you are getting a series like this, that is f0 plus x f prime 0 and so on. This is nothing but the Maclaurin series. And now your focus function is e to the power x, right? So you can expand e to the power x in terms of a polynomial using this Maclaurin series. But interestingly, this particular function e to the power x at x equal to 0, because this is a prime sub 0, all are zeros, no, isn't? In that case, e to the power 0 is 1. Not only that, any order derivative of fx e to the power x is actually e to the power x, and e to the power 0 at x equal to 0, it is 1. So all these f0 and f prime 0 and double prime 0 in red color all are 1. So it remains only the blue colors, right? So here 1 you will get 1, then x into 1, then x square by factorial 2 into 1, then x to the power cube by factorial 3 into 1. So you are getting an expansion of e to the power x as this expansion series, right? Now it's a matter of computation. If you do, it would give you the value or exact value 2.7182818285. So that also you can check whether your expansion is correct or not, how far Taylor series is valid, and efficient in evaluating the e to the power x function, how many terms are required, etc., that you can explore by means of another program. So let me run another program, and that is e to the power x by Maclaurin. Okay, so by Maclaurin, e to the power x by Maclaurin. That means I will be using an expansion as I have shown to you. So I will be running this program, and this time it would not give ask for the it would ask for x value, because I can give x once 1 like the earlier case, and of course I can use the same expansion for e to the power pi also, that is Goldfriend's constant. So let me give x equal to 1, and this time the number of terms let it be very small, 15 only, and you see the result is excellent. 2.718, 2.718, 28. So up to 5th place is exactly the same, right? Not even 6th place. So it is of course much more efficient expansion. It converges very fast, but it is giving the very close value, right? And now again I will run to get that constant, Gelfond's constant, and this time I will give the value of x to be 3.14. So 3.14, and again you give just 15, and you should expect that 23.14 is the exact value, 1.06, 1.406 up to 4th place it is exactly the same. So that in both the cases we have seen that this is a better method, better expansion actually, and we have explored both the method, Maclaurin's method and the bank interest method, you can say. And now again I am going back to my presentation. Well, we have explored e to the power pi, because e and pi both are transcendental numbers, so e to the power is also. Then of course you can be tempted to ask that why not I, another very peculiar awesome number I, and moreover e to the power I pi. So you can see that I am giving a hint towards something very interesting, something very famous, important, and that is the most beautiful equation. Actually, we call it e to the power I pi plus 1 equals to 0. That means e to the power I pi is minus 1. So that is one thing we will explore again. But before that, I will very quickly get the outline of how Euler got this beautiful expression, again using the starting from the Taylor and Maclaurin. So as I have shown you that e to the power x is this kind of expansion, and what Euler did, he replaced this x by some iy, some imaginary quantity, so e to the power iy, right? And you just replace x by iy, so x square, that means iy whole square, and so on. So as you know, I square is minus 1, and accordingly you can get e to the power I pi is 1 plus iy minus y square by factorial 2, and so on. And deliberately I have used some two different colors. You see the red ones without having I, and the black ones having I plus or minus. So what next Euler did, he grouped these total terms in two groups, the red ones and the black ones, I taking common, so that at that time it was not quite known to them that whether you can group from an infinite series in this way or not, but Euler did it with his high level of intuition, and that clicked. Anyway, this red part actually the expansion of cos y. That can be shown again by using the same Maclaurin expansion as we have used for e to the power x. And the black part is nothing but sin y. So it gives actually e to the power iy is this cos y plus I and then sin y. So I and sin y. And now if you put just y equal to pi, you will get e to the power I pi is cos pi plus I sin pi and minus 1 plus 0. So e to the power I pi is minus 1. So that is how Euler intuitively, with a little bit of faith in his intuition and his mathematical insight, he got this formula e to the power I pi equal to minus 1. But that is not our target in today's session. Rather, we will try to have this most beautiful equation from bank interest problem, right? Again the same bank interest problem. That means we will be using this series e to the power x equal to 1 plus x by n whole to the power n for large n. Now if you want x to be replaced by I pi, then you just replace here x is I pi. So it looks like this, fine. So you have to compute this quantity, but the problem is that this requires a lot of complex algebra. Now handling complex algebra is not impossible in ForTran, but it's very difficult and you have to be very careful. Well, we have tried it, and what we expect, this whole thing is a complex thing because I is there, so the result should be a complex number, but the final result we know that is minus 1. That means minus 1 in complex format, it is minus 1 and 0. The real part is minus 1, the imaginary part is 0. So if we evaluate this quantity, we are expecting that the result will be a complex number like this. If it happens so, then we will say that okay, it is verified by our programming. So that would be my next program, the last one. So I am now computing e to the power I pi. Okay, this is my problem. I will just give a few words on handling complex. Here you see implicit complex. I have defined all the variables starting from a to h and o to z implicitly to be complex. The whole program is in complex mode, except that some of the functions, some of the variables are declared to be real, x, xr, and so everything in terms of x, because x is e to the power x. So I will be giving pi value. No? So pi is a real quantity. We don't need to give as a complex number. So they are real number. And then how I am giving the pi value? It is tan inverse. That means pi by 4. A tan means tan inverse. Pi by 4 into 4. So it is pi. So x is pi, and that is evaluated a tan 1.0 star 4.0. And then I am giving some maximum value, maximum number of that n value, and then I am evaluating in the next part that quantity 1 plus I x by m whole to the power m. So you know within this bracket, third bracket, this quantity is a complex quantity, right? And real part is 1 and imaginary part is x by m. So that's why I am defining f1 as CMPLX, that means converting a number to a complex given this format, that it takes up only the real value separately separated by a comma, and then the imaginary part, and imaginary part is nothing but x by m. So x by m, float m to make it a real number. Okay, so this is my f1, that means this quantity, and now to the power m. So f2 is that quantity, f1 to the power m, double star m. So now I am calculating it for number of m values, but I am displaying as a result the last value m and f2 after the loop is over. So that is what I am doing, and finally after getting the values, I am retrieving that real and imaginary part separately from that complex number in this portion, and after getting this x real one and x im, that means x imaginary one, by some logic I am retrieving, and then I am just making a final approximation display for approximation. That means I am saying that if the value is 0.0005 say, for example, then let me treat it as 1, and on the other end the imaginary part, which I suppose it comes to be 0. So I say that if it is less than a very small number, 5 into 10 to the power 5, then you may treat or consider it to be 0. So as a final approximation, it would write -1 and 0, provided it satisfies these conditions. Okay, so with this much, let me run the program. So this time it will just ask for a max, and I will give some value, say again 2000, maybe in the earlier case I put 2000. So I will check whether it gives you the complex number with imaginary and real parts separately, and so well. So let me give 2000. You can give even more, and you see the result is coming as, by default it shows this result. That means it gives a complex value whose real part is this and imaginary part is this. So now I think we will agree that if I can increase the value of this max, so I will go even more close to -1. So according to my approximation criteria, it is reporting as -1, and it is, you see, 10 to the -6. So it's very small, and I'm considering approximating it to be 0. So the final approximation result, it displays its -1 and 0. So e to the power I pi gives -1. So that is also a beautiful exploration in the language of course Excel and ForTran. Now well, if you are ready to call this picture as one of the most beautiful face, of course you can. It is the picture of Audrey Hepburn, one of the all-time most beautiful lady. And if you are ready to call even Dada's off drive to be one of the most beautiful something on the heaven or on the world, then why not a beautiful equation, e to the power I pi plus 1 equals to 0. Okay, most of the mathematicians and physicists, they agreed that yes, they can call it this as the most beautiful equation because of so many attributes of this equation. I am not going into that explanation, but yes, this is one of the most beautiful formula in the world. And of course, we have explored this beauty in the language of Excel, ForTran, and of course to some extent maths. So that's all for today. Thank you for watching. I'll be happy if you please come back with some suggestions and comments. Thank you.